Hello, everybody. It's April 20th. April 20th, 2020. Basically, it's 4/20/20 today. The crazy part is, I can't believe it is already April 20th. And I was looking at the calendar yesterday, and pretty much we have like a month and a half of school left, right? It's insane how this is sort of happening. Just to think about like a month ago, over a month ago, like we didn't even see this, and we were just thinking about it. And now we've been home for like 4 weeks, I think. Oh my goodness, I think it's starting to affect everybody, right? Like the anxiety and just like being at home and just like not being able to go out. Some people are like, I can't, like it's yeah, it's concerning sometimes, right? Like to think like we're always home, and but I think we have to I think it's there's a light at the end of the tunnel. I think our in Manitoba, like the cases have gone down quite a bit, and the curve is sort of flattening, and maybe we'll come back to school sometime in June, because I mean in the past 7 days the cases have been very low, right? So it's pretty neat to see that in Manitoba. So I think it's important for us to keep going. And I think this online streaming and classes have starting to become like a routine for some of us, right? Sitting in front of a computer and just talk in front of the computer and connect through with people through the computer. I don't know how you guys are feeling about this. Obviously, you guys probably have been staying home as well. Um, Let me know in the chat, but it's good to see you. I miss all of you. I miss being in the classroom. I miss making fun of some of you, just some of you. I miss doing labs and demos with you. I don't know. I think it's sometimes it's been hard for us, like for me and my family as well, because I feel like I'm neglecting my own kids, because when we're sitting here, like my wife is also a teacher, so in the morning, it's like both of us are in front of our computers, and what do we do with our own kids, right? And they're just watching TV. And my 5-year old, I've taught her, initially it was kind of cool because I taught her how to play Mario Kart. Initially it was just like, hey, let's play this game on Wii U, and it's cool, and it's Mario Kart. And before she was terrible at it. Now she's playing so much that she's actually pretty decent. Like, obviously she's not at like 200cc or 250cc level. She's still playing 50cc, but she's getting, first place in these cups. I was like, wow, that means that you've been playing a lot of video games. But yeah, like it seems like it's just, I don't know. I feel like I'm neglecting my own kids. I don't know why I'm sharing this with you, but I feel like I haven't talked to anybody except for my own family, and that's it. I don't even see my parents now because, yeah, because they're like at a older age, and I don't want them to catch anything, or that they're going out as well. I don't want my kids to get anything, but yeah, I'm sure it's tough for all of you. But I think it's gonna be over soon. I don't know. It seems like Manitoba's doing quite well with all the low cases, and I mean, I can't see us closing down the schools like till the end of June if our cases remain like 0 or 2 for the next 2 weeks, right? Because I think we're doing quite well. But I hope all of you guys are doing quite well. The classroom, I don't know if you've been to the school. If you need to pick up stuff at the school, you need to register for a date or a time, because it's like you go in and you get your stuff and you have to leave kind of thing. So make sure you do that. My classroom right now, went in. I think I told you, like it's like a mess. I don't know if I told you. Some of you, I don't know if Marwan and Jabir are here, and also Guy, because you guys always look at my fish. I have terrible news to tell you. Um, Last week I took all the fish home, and then none of them survived. Not very funny, but because I wasn't gonna go to school like every week to feed them or to top off the water. But so I took all the fish home. I brought that tiny fish tank home as well, and then I put all the like I pour the bucket of water from the fish tank, so it's like same water, and then I filled it not, I didn't even fill it all the way. It was just half. It was I just filled it about half with water, and then one fish started to float, and then like a couple hours another fish started to float, and then the whole tank died. I don't know if somebody spread the disease. You guys are gonna make me cry here because all those crying emoticons. But yeah, so the whole fish tank is done. But one thing though, I have to say is that that big Dalmatian fish that's always been hiding, I wasn't able to catch that big fish. So that fish, I left that fish in the fish tank. Unfortunately, though, I think that fish is not going to make it because I had to unplug everything, right? So the filters were unplugged, all the lights were unplugged. So it's basically just still water in that fish tank. And I don't know if that fish makes it. That fish is gonna be like genetically modified and some mutant that can survive with no oxygen or hardly any oxygen, no food, maybe just from the algae. But yeah, so just so you know, maybe when we come back, maybe next year we can all chip in and make a new fish tank with a new fish community. I was thinking of making that into like a hydroponic where like we can grow plants at the top, and then put fish underneath. I've been thinking about this. I did this. I did this like I think a couple years ago, but I want to make it better. So in terms of Isla, I want to be extra to make it better. So hopefully, hopefully, the fish tank will be a little bit better. All right. Yeah. Let me. I love seeing your chats because it makes me feel like you're here and connect with me. Otherwise, I'm just like ranting and having this vlog of like, oh my goodness, what's happening to my life kind of thing. But keep typing. I'm actually reading. Every time I look on that side, it's really just me reading. All right. Yeah, I know. Hey, I did leave the fish, but all right. We're done second unit. We're done that gas laws unit. Hopefully a lot of you have did that quiz. I totally want to apologize for those two errors. Error number 1 was that 1.5. All those 5 should be 1.7. I did change it after, but I don't think it got updated on the forums. And number 2, there was that answer error about yeah, there was one. I can't tell you the answer right now, but there's one that I had to I've been manually going to everybody's quizzes and changing the marks, so don't worry about it. I do go in and see, but thanks for emailing me. The thing is, like, all those Google forms that you guys, or not Google forms, but like Microsoft forms that you've been doing, like I have to retype all those questions on the forms, and then I have to like quickly do the answer key. So sometimes I'm just like, hey, I'm just gonna do this in my head, do all the manipulation and isolating my head and put it onto my calculator, and as you can tell, you can make mistakes. So thanks for correcting and letting me know on that, even though I got like 6 emails all at the same time. But good stuff. Okay, today's lesson is just, I want to go through the new unit. So this is unit 3. It's called chemical reactions. It's all about sort of how reactions occur, or I should say really looking at the nitty-gritty details of the calculations and reactions. How do we determine the exact amount of something? Okay, so I have updated your class notebook. So this is on your Teams. If you click on class notebook, unit 3 is right here. I have all of the notes posted here, and also I have done a tutorial video for everything in this unit because this is by far the most important unit in grade 11 chemistry. So you can see that it's like you're naming stuff, which we have already done, and then there's like balancing reactions, types of reactions. So then this gives you like the background and theory of how reactions occur, what type of reactions happen. And then the next most important part here is the mole stuff, because moles actually provide us with the exact calculations of how much stuff do we have. So if we were to make drugs, right, if we were to make drugs, because sometimes people think chemistry is about, profiting from making drugs. Yeah, if you go into pharmacy and be a pharmacist, absolutely. Well, you have to know the exact amount of things to mix together to get that product, right? If you ever seen Breaking Bad, right? Jesse and Heisenberg, the difference between those two, well, Heisenberg is a chem teacher and know how to do this exactly, right? Very accurate and also precise. Whereas Jesse Pinkman, I don't know if you guys seen this, but I'm just saying, like, the guy who also made drugs wasn't very very good at chemistry, but he just followed recipes. Anyways, if you want to become a pharmacist, this is probably very important, because it's all the exact calculation to get the exact product. Also, not just in drugs, but like manufacturing. If anytime you want to make something, make some sort of chemical, make some of compound or molecules, right, in mass production, right, you're gonna mix A and B together, but you can't just say, oh, I'm gonna throw some amount of A and some amount of B together, and you're gonna get something. Well, because each of these costs money, right? So you don't want to waste that. So for this unit, it tells you the moles. It tells you that how much of this and how much of this you need exactly to make your final product. So this is actually a very important unit. And if you watch Breaking Bad, like, we talk about this in grade 12 as well, because Breaking Bad is actually really clever. Like the character Heisenberg is not just like some random name. If you go into grade 12 chemistry, when we start talking about like quantum mechanics, Heisenberg, if you search up Werner Heisenberg, he actually came up with this uncertainty principle, and I think that's the reason why Walter White has that name, Heisenberg, because of his character. But we can talk about it when we get into grade 12, and I feel like talking about that in person, because I think it makes so much more sense. All right, so moving on. Again, I have tutorial videos for all of these, so anytime you get stuck, totally go back and go into this. And I also put the work booklet into your teams as well, just like before. So let's just kind of go through the first one. So the first thing I want you guys to take out is your periodic table in front of you. And your periodic table is a very interesting thing, because everything that exists in our universe is on your periodic table, right? That's the one thing that I never appreciated when I learned chemistry, because, when I learned chemistry, it was just like, hey, here's a periodic table, here's the elements. But I never realized that everything that you're sitting on, looking at, touching, inside your body, star stuff, star dust, right? Everything that exists are found on that periodic table. So from the stuff that's in your batteries, to the monitor screens that's in front of us, right? To plastic, right? Everything, even the things you eat, the molecules, right? Everything, right? So that's the really cool part about the periodic table. But the thing is, though, when we think about the periodic table, what happened to my screen, is that if you take a look at it right now, there is this number. So there's two numbers on your periodic table. One is called your atomic number, and one is called the atomic mass, right? So there is a sort of a decimal number, which is your atomic mass. There is a whole number, which is your atomic number. So this is your right here. Let me see if I can draw this one. This is your atomic number, right here. This is your atomic number. So remember, your atomic number is really just the number of protons. If you remember in your atom, right, there's the positive protons, there's the negative electrons, right? To be 100% certain, your atomic number is just the number of positive protons. We don't really say it's the number of electrons, because sometimes you have ions that have one more or one less, or two or three less electrons. Remember, electrons, the negative ones, right, that can be lost or gained to give you that ion, right? Like if you think about like K plus, right, this is an ion. Or if you have oxygen 2 negative, this is an ion, because this one is saying that it's going to gain 2 electrons. Potassium, this one K plus, is lost 1 electron, right? So when you're looking at the atomic number, this is just the number of protons, okay? This is just the positive, because you can't add or lose protons, all right? So that's your atomic number. That's very important in a sense, because it identifies your atom. The next one is that your atomic mass is your decimal number. So here's the question. I don't know if you ever noticed this. If you ever gone to a party, like a chemistry party or like a science party, super fun, and then you guys start talking about the periodic table, and then someone gets up and say, hey, I noticed that there are decimal numbers in the atomic mass, but no decimal numbers in the protons, right? How come there are decimal numbers for this one? If this is a mass, right, this is how heavy it weighs, right? If this is carbon, chunk of carbon, this is how heavy it weighs, right? How come that there are decimal numbers? This is something to wonder. If you ever get a chance to go to science parties, I think it's great. You should totally host some science parties after this, because then people talk about science, people talk about like smart things. It's great. All right. Any ideas why there's a decimal number, right? Well, the decimal number is really derived from the average of the isotopes. So if you think about all the existing, say for this example, carbon doesn't just exist in one form. Carbon can exist in multiple different forms. You might have heard of like carbon 14 dating, right? So in carbon, there's actually two forms that exist. That's carbon 12 and carbon 13. And what that means is that the protons actually will stay the same, right? Because like if you think about your atom, if you were to look at your Bohr model, right? So this is your Bohr model. All of your electrons, let me just kind of change colors. So all of your electrons on the outside, right? All you have drawn these ones, right? All of your electrons on the outside, and then you have your protons on the inside, right? So your protons, your positive, stay in the middle, right? And then to make up the mass of this number, right? This number, it's actually your protons plus neutrons. So it's actually your P, your protons plus neutrons, and then this will give you the mass of how heavy your element is. But in nature, you don't just have one version of this. You actually can have different versions. So say this carbon 13 is also another version of carbon. So why is it still carbon, even though it has a different mass? Well, it has the same proton. It has the same number of protons. So it's like your carbon 12 here has 12 protons, right? And then carbon 13 also has 12 protons, because the protons make up what the element is. Well, how do we get the difference of the mass? Well, this is where you have your different number of neutrons. So neutrons are also found in a nucleus, and they're heavy. They don't have a charge, but in carbon 13 you have 13 neutrons instead of, or I'm doing this math totally wrong. Hold on a second, I'm talking too fast here. Let me just backtrack here. Carbon has 6 protons. You probably were correcting me as you were watching this. Totally. I'm just kind of got caught up here. 6 protons. Let me clarify that. Carbon has 6 protons, as it's stated here. In order to get your 12 mass, you have 6 neutrons. 6 plus 6 is equal to 12, right? This is also carbon because it has 6 protons, but in order to get to 13, it doesn't have 6 neutrons anymore, it has 7 neutrons. So if you add these two numbers together, you have 13, the mass, right? So both of these are still carbon, just different versions of that. I don't know if I explained that correctly. I just wanted to be extra clear. I don't know if I messed you up by saying 12 protons here, but this is the mass. This is also the mass, right? There's 2 different variations of carbon. One is carbon 12, one is carbon 13. Both of these are sort of your isotopes. So when we calculate the number of, if you look into your periodic table, carbon actually has the number of 12.011, right? Let me see, 12.011, right? Where is this number from? So when we calculate the average atomic mass, it's just like calculating your final grade. Okay, so this is how your final grade is calculated. This is just an example, right? If you look at this entire block here, this is what your final grade is from, right? 25% of that entire block goes into your exams, and then you have 70% of your in-class work will get attributed to your final grade, and then also your 5% on labs will go into there. So the question here is that, well, if you got 80% on your exam, so 80% of your 25, 60% of your 70, 90% of your 5, what is your final grade, right? Are you going to add all these numbers as in equal parts? You're not, right? Because exams are only worth 25% and classwork is worth a lot. So even if you get, say, 100% on your exams and maybe like 50, you can still get a sort of a crappy mark because you only got 50% of your classwork, right? So if you were to look at this example, how would you calculate this? Let me just kind of erase all these marks and then I can show you, right? So in order to calculate all of this, where is my mark? Hold on a second. Let me reset my pen here. So if you look at this, I'm gonna look at, well, how much of this 25% is 80%. So I'm gonna do this. I'm gonna take 80% and then I'm gonna multiply by 25%. But here's the thing, I'm not gonna keep the percentage, I'm gonna put this into decimals. So this is, if I change this into decimals, I'm gonna move it over. So this is gonna be 0.8 times 25. I'm just gonna leave it as 25. And if you look at that, let me get my trusty calculator. I don't wanna do this on a mental math in case I do this wrong again. Times 0.8 is 20. Okay, where did my pen go? So this is 20. So if you get 80% of the 25%, you actually get 20 or 20%. So then you got 60% in your classwork. So what you're going to do is that you're going to take this 0.6 multiply by 70, and then what you're going to get is going to be what, like 42? I just want to double check my math right now, just in case. Yeah, it is 42. So this is going to be 42%. And then lastly, you did really well, 90% of your labs, but your labs are only worth 5%. So what you're going to do is you're going to convert that 0.05 times 90. And then this is going to be, again, I think it's going to be like 4.5, but I don't want to, yeah, it's 4.5. I just want to double check my math today. So then once you have all this stuff, right? What you're going to do is that each of these are going to contribute to your final grade, right? So you're going to add them together. 20 plus 42 plus 4.5. This is how you calculate for your final grade. So your final mark here is what? 6.5%, right? Even though you did very well in your labs, you did pretty decent on your exam, but you didn't do so well in your classroom. So why did I go over this example? This is exactly how you would calculate average atomic mass, because in your average atomic mass, to get that final number here, this number is the average atomic mass of all the isotopes. Basically, it's just looking at the average mark of all of your different chunks of your grade. Okay, so here's an example. I can't really cover all of this, but let's go over this example and just kind of look at here. 98.892 of all carbon atoms are carbon-12 and has a mass of this. So if you were to look at this big bar of the entire carbons, 98% of this, 98.892% of this is going to have a mass of 12.00 atomic mass unit, just like 98% of your grade, right? And then the next one is that 1.108 here. I'm just going to write here 1.108% of all carbons will have carbon 13. So here's the 13.00335 AMU, atomic mass unit. So how would you calculate this? So because you can see that the 12.00 AMU takes a bigger chunk of this entire mass, you need to figure out, well, how much of this is going to get accounted for. So the first thing is that you're going to take the percentage, 98.892% times 12.00 AMU, right? So of course, you're going to change this into decimal numbers. So this is going to be 0.98892 times, this is going to be off screen here, boop, right here. And then we're going to times this by 12. And then you're going to get a number that's really close to the 11. So this one I can't do this in my head. So give this a try. 98892 times 12, and you're gonna get a number of 12. Well, not 12. What am I saying? I can't even erase it because I can't see on the screen. 11.86704. Leave all the decimal numbers because this is going to be your average atomic mass for your atomic mass. You want everything to be very, very precise here. So this is going to be your AMU, your atomic mass unit. Then we have to figure out the next one, which is your 1.108% right here. So we're going to take that 1.108% times this by the mass of the 13. So that's going to be 13.00, I think, is it 335 right here. It's on the left side. And of course, I'm going to change this into decimal. Remember, you're moving this 2 times to the left, so I'm going to be 0.1108 times 13.00335, right? So then I'm going to multiply all of this stuff. So I'm going to put this on my calculator. 0.01108 times 13.00335, and I'm going to get a number of 0.144077118. You notice it's a very small number because it actually contributed very, very small, a minute amount. So the last thing I have to do is, just like your grade, I have to combine all of these sections or chunks. So I'm going to add these two numbers together, and if you add these two numbers together, you should get 12.011 AMU. And if you look at this number, this is the same number that you'll find on your periodic table, because that's the average atomic mass of all of the occurring isotopes naturally on Earth. Okay, does that make sense about calculating this? So I'll leave this up for 30 seconds or less and let you kind of check this out. And then if you haven't said hi or said anything in the text box, can you just say like, hi, what's up, so I know who's here, right? It's just like for me to know who's here. That would be helpful. So then it's like taking attendance. Okay, example 2. Oh, I don't want to maximize the screen here. Where's my mouse button? Let me do this again. Example 2. So example 2 is that there are 2 different types of isotopes of copper atoms. So one type is this amount. This is how much one type weighs. And the other one is this amount. And the lighter isotope is more common with 69.09, and then has a mass of this. And then the heavier one has just 30%. Awesome. Thanks. Cool. Awesome. Good to see all of you. So then what you're going to do here is that you're going to do exactly the same thing. You're going to take the percentage here. You're going to multiply by this. I think the math here is not too bad once you try a couple times. And then take this percentage and then multiply it into this. And then you're going to add them all together. Okay. Once you have added them all together, your number should be the average atomic mass or your atomic mass on your periodic table. Pretty neat, right? That's how that's where that decimal number is from on your atomic mass. So like today you have just learned why there are decimal numbers on your periodic table instead of whole numbers. I think that's worth sharing to the world. I think that's pretty cool. Just to finish this up, isotopes, we keep mentioning isotopes. Basically they're the same element, but they have different number of neutrons. So that's why they have different masses, because the proton stays the same, because again, protons define the element. The neutrons is also found, but just have a different number of them in the nucleus. Okay, so atomic numbers, but different mass numbers, because the mass number is the protons plus neutrons, which we have talked about already. Okay, and yeah, this is how isotopes can be represented. So these are all isotopes. Some of them are radioactive and they have a half-life that will just kind of depreciate half of it over time. Again, some of them are radioactive that they don't just stay there and stay stagnant. They will decay, which is also pretty cool. That's why that's the radiation that's being emitted, right? So that's the first lesson. This is all I wanted to share with you today. And what I would ask you guys to do is that I'm going to have you work on the first 2 pages of this. So if you look at the work notebook, oops, I totally moved it out of the way. Let's go to your work notebook. I think there's 2 pages of this. Let me kind of open this up. Work booklet. Right here. And then I don't know what page, we'll just kind of have to scroll down here. Let's see what page it is on. Yeah, page 61. So if you want to go to page 61, it's still loading on my screen. Hi everybody. It's good to see so many people here. That's pretty good. Still loading, still loading. Come on now. A couple more pages down. So what I would ask you guys to do now is that, not even on page 61. Oh, I think I missed the pages here. Let me just keep scrolling. Look at all the work we've done. Okay. Gas laws, conceptual questions. Here, page 77. So work on page 77 because I don't want to spend, oh, come on. Exceeds drawn dimensions. What does that mean? Work on page 77. And then also page 78 for Wednesday. It's really, really short. It's just like 10 questions of this. This is something that I don't want to spend too much time on. It is important, but it's not really that like crazy important. So I don't want to spend like after Wednesday, we're just going to move on. We're not going to come back to this after this. Okay. So, do page 77 and 78. I can't seem to write on this, so I can't mark it down, but 77 and 78, I'll put it onto your OneNote, not OneNote, onto Teams. But after Wednesday, we're going to move on and we'll go do a little bit of review, but then we're going to talk about types of reactions. That's it. That's all I wanted to talk to you guys about. If you have any questions, let me know. I'm just going to put this up onto Teams right now, okay? So this is going to be page 77 and page 78 for Wednesday. 77 number 1. You want me to do the first one? Okay, let's see if we can bring this back up. It's kind of slow. Now we have to find 77 again. Come on, teams. She's like, is it somewhere here? Okay, we'll just have to wait for this to load. Does anyone have a joke or anything while this loads? Or any information you want to share with everybody? Oh, this is only page 59. Okay, let's scroll down to 77. Okay, so this one, yes, if chlorine has 2 natural occurring isotopes, I don't know if I can write on this one though. That's too bad. Why? Please draw within the border. What does that mean? Like I can't. I gotta figure this out. I don't know why. So, sorry, Chloe. I don't know why I can't draw on this one. Like I think it's like too big of a file. I would have to come back and look at this. So what you would have to do here is that you're gonna take, because both of these chlorine atoms contribute to the entire average atomic mass, right? So this chlorine 35, has a mass of 34.96, etc. But it makes up a bigger chunk, right? But even though it makes up a bigger chunk, it's not the entire chunk. So you have to calculate how much of this do you have. So 34.96, you're going to multiply this number by 0.7577, and then keep that number. And then the next one is that this 37, like this chlorine 37, has this mass, but it only takes up that 24% chunk. But that's still a chunk that contributes to the entire whole. So you have to take this, multiply by the decimal number of this, So then once you have calculated both of those or multiply both of those numbers, then you're going to combine those. So this number times this one, you're going to get a number. You're going to add that into this and this when they're multiplied together. And when they're multiplied together, you should get that average atomic mass that's on your periodic table, which is what, 35.45 or something like that. So that's how you want to do that. Again, I can't really write on this. I don't know why. It kind of sucks. But I'm going to try to figure out why I can't write on this. But hopefully that did answer your question, Chloe. Okay. All right. Marina's dog says hello. I don't know why. Like, June, what does that fire in the toilet mean? This is good. If there are no other questions, that's all. I'll see you on Wednesday. Again, all of this, if you need help, the tutorial videos are here as well on your OneNote class notebook, right? So it's at the bottom here, unit tutorial videos. So if you want to watch another tutorial video just to clarify your information, understanding, it's there as well. Okay. So I'll see you. 2 isotopes of helium. Hee. Right? Yeah? Did I get it? Too bad there is that delay. I feel like I'm still waiting, but I think it is hee. Yeah, I got it. Okay. I'll see y'all. Bye. End the stream here.